All right, just testing, making sure everything's working here. Test, test. All right, that looks good. Cool. All right, gonna share my screen here and we can get going. Cool. So yeah, today we're gonna be, well, I was planning to work a bit more on this Chow multi-tool project that I've been working on, but I figured today could also be a little bit of a wild card day in case folks have other things they want to, I don't know, see me talk about or work on. Could do some circuit modeling, some other physical modeling, some more generic DSP stuff or optimization. Yeah, whatever people are interested in. But yeah, I guess I'll start off by showing where we are with the project right now. Let's get this guy going here. We'll make sure everything's up to date and rerun CMake. So I should make sure my name is, well, yeah, I'll try to change my name here. Rename. Cool. Yes. All right. Yeah, so let's build and see where we're at. All right, yeah, so what I was working on most recently is messing a little bit with the Pultec EQ. So I'll show you guys that very briefly here. So let's see, where are we? Okay, here we are. Yeah, so the Pultec circuit that I've been using as my reference is here. What's going on here? Just want to copy this link. All right. Anyway. Cool. Yeah, so this is the reference circuit that I've been going off of. And yeah, for anyone who is not familiar with the Pultec EQ, this is the one that I'm talking about here. Hopefully this is a nice and large picture. Okay, yeah, good enough. Yeah, so the way that this EQ works is that you've got some of these continuous sliders to control the gain of the different frequency bands, and then to control the frequencies of those bands, you've got these sort of stepped knobs or stepped switches that you can use to step between different frequencies. And you can kind of see that here in the circuit as well. So for example, this boost low, this is the switch that picks, oh, sorry, that's the boost low potentiometer. The high cut F text here is referring to this switch. And so that could be either at 20 kilohertz, 10 kilohertz, or 5 kilohertz. And then there's a similar thing here with the low frequency selector, switching between these sets of capacitors. And same thing with the high boost frequency up here, switching between some different capacitors and inductors over there. And kind of what I was thinking with this is that, you know, the original circuit was kind of limited to having these stepped switches because at the time you couldn't get a variable capacitor, or at least it must have been very difficult, I imagine. And so that's why they chose to design it this way. But you know, in our software model, we can make a variable capacitor quite easily if we want to. So I figured I might try to make these controls continuous rather than stepped. So that's what I was working on most recently. So let's see what that looks like in the plugin. We're in debug mode here. All right. So we've got plugin pulled up here. And yeah, so here, if we look at the Pultec EQ, also made the UI resizable, not that that really matters too much for right now. But you can see here, we've got these frequency controls, which are now sliders rather than like a combo box or something like that in the juice terminology. And so now let's maybe boost some bass frequencies. And now if we want to, we can control the frequency continuously, which is kind of neat. Yeah, so now this is all, these are all continuous controls. So, you know, we could do our low frequency cut and that all gets shifted around as well. And then maybe if we want to look at the high frequencies, we've got our treble cut and our treble boost. And again, we can shift these around continuously. We can do that with the treble cut as well. So yeah, it's kind of a neat thing to be able to do. So one thing that I was going to look at doing today is putting together some controls that would be on this frequency plot that would allow us to control the parameters rather than the sliders here. So it'd be a little bit more like a typical EQ control. Let's look at some other EQs here. Let's see. Like for example, the classic fab filter. So with fab filter, you've got this little we'll call it I don't know, I call it a boat down here at the bottom with all these extra controls. But up here you've got your frequency and your gain as kind of this 2D control. So maybe something like that would be an interesting thing to do. I think there's also a modifier. Yeah, okay. On Mac it's command. There's a modifier for changing your Q value. On the Pultec, only the treble boost has an actual Q parameter, so we can see that here. It's a little bit hard to see at that frequency, maybe. Yeah, maybe I need to fiddle with that a little more. I've also been noticing some inconsistencies in my my frequency plot here, so I might need to improve on that as well. I'll give you an example there. Yeah, so this is what shows up in the EQ curve analyzer for the same process here. So I don't know, I might be doing a little bit too much band smoothing up at the top end there. Yeah, just some random little things like that I think could probably be improved. So yeah, you can see that the Q actually does make a fairly big difference, but it's not really showing up on the plot here. So yeah, I think that's a little too much band smoothing. So yeah, let's see. These are some of my notes for today. So let's see. For today, we're going to look at Pultec EQ controls, maybe presets, getting that going. I don't know, maybe something else. Sorry, I have my window open and a truck is driving by. I'm going to close the window real quick. Oh yeah, and also I forgot the Pultec EQ plot. Was it? Wait, right. So yeah, those are a few things for us to work on today. Yeah, unless anyone else has some ideas or things that they'd like to see me talk about, I'd be happy to talk about whatever today. I'm kind of feeling a little bit I don't know, I'm in the mood for a wild card kind of thing. So yeah, I'm happy to happy to drop any of this and do something else if people are into it. But yeah, so maybe let's think about the Pultec EQ a little bit. Yeah, so maybe just one thing we could try out real quick is for the filter plotter, it was changing the frequency smooth octaves. So the default here is, I believe it's 1/12 octave band smoothing, I think is the default. Can't seem to find the definition for me. That's annoying. We can find it ourselves. So here we go. This is in the generic filter plotter. Yeah, so we're doing 1/12. Even that's pretty narrow, but maybe we can go even narrower. Maybe we want 1/36 or something, and it probably needs to be floats. Yep, thanks for the warning check there. Yeah, so let's try that and just see what comes up. Okay, George wants to talk about pointers. Pointers are always a good thing to review. Yeah, maybe we can do some pointers talk. Yeah, that actually might be interesting too, to talk about some things with optimization. That would be interesting. Cool. Yeah, maybe we'll do some pointers talk. That would be fun. Here at both the EQ curve analyzer and our EQ curve. So let's see, we're plotting from 30 to -30, or really from -30 to 30, I usually think about it. So that's 10. So maybe we're at like 12 dB or something, whereas the EQ curve analyzer is showing something a little more like, what's that, 18 dB? Okay, yeah, so we've got a bit more thinking to do on that. Anyway, maybe I'll leave that for now and come back to it later. I don't really have a exact idea of what to change there at the moment. But yeah, maybe let's talk about pointers. So yeah, here, create a new project just to talk about this with. So let's see, I'll put this under research. I don't know. Sure, whatever, research pointers. And we'll do C++ 20 because I like C++ 20. So yeah, this is just a fresh C++ with CMake project. I'll put them playing tidy because I like, I just like to have it. Oh, not playing tidy, playing format is what I wanted. I mean, I don't know, playing tidy is nice to have too. But yeah, so that's just the style that I'm used to. So yeah, right now we've just got a simple CMake project with a main file here. So the idea with a pointer, this was kind of the sort of basic stuff that I learned when I was first learning C++. So we start with maybe an int x equals 0, and then you know, we can let me do a couple other things here. So, well, yeah, I'll do it. I've been using lib format a lot lately, so I'm gonna bring that in and CPM as well, just because I'm used to it. At some point I should make a template for this stuff. But yeah, so for those who don't know CPM, it's pretty nice, just a little like package manager for C++. So I'll just use that here. File. Usually I use version 0.7.0, and then I've got a, yeah, again, I should make a template for this because it's kind of annoying to have to do all the time, but whatever. Yeah, so for those who don't know, lib format, it's just kind of a nicer way of printing stuff, basically, that's maybe a little bit more similar to what you might see in Python or things like that. So yeah, we're going to link to that here. Yeah, I guess why did they abbreviate it like that is my question, but yeah, maybe that's about my pay grade. Anyway, so we'll rerun CMake and then we can do some format stuff. Oh, I spelled it wrong. Include, there we go. Cool, so we're gonna add the format package, and then we don't want IOStream, we want or I guess, yeah, so we'll do, let's see, format print, and so we'll print integer that address, and so we'll have X and we'll have the address of X. And so when we run this, this will show us, what did I do wrong here? Formatting of non-void pointers is disallowed. Oh, interesting. Okay. Maybe I need to cast this static cast. I don't know. I'm gonna let me do that. Static cast from int star is not allowed. Maybe this needs to be a standard pointer, something like that. No. Interesting. It doesn't seem to want to let me print a raw thing. What if I do an implicit cast? Okay, it's happy with the implicit cast. Not totally sure why that is, but anyway. Yeah, so what we're able to see here is we're able to see our integer, which when we print the integer, we get the values. This is the value 0, which makes sense. And then here we can see the address in memory where 0 is stored. And so that's nice because, you know, we've got our address. And so when we say we have a pointer, basically what we're saying is we have the address of the variable in memory. And we can actually see that here. We can make an int pointer, and we'll call this x pointer, and we'll set it equal to x. And we'll print x pointer here instead. Right. So if we run it, we should get, you know, about the same thing. So hopefully that makes sense to everyone. And so I'm actually going to extract this to a little helper function here. So we'll, oh yeah, someone's asked me to zoom in. I've been doing that on the live streams, but I forgot to do it today. So thanks for the reminder. Okay. We'll make the menu stuff bigger, and then we'll make the editor font bigger as well. Cool. yeah, if you want me to go even bigger, just let me know. I can do that as well. So what we'll do here is we'll make a type name, and we'll make this a void function. And so we'll say print value and pointer, and we'll have a t value. Actually, maybe we should have a const reference to t. And what we'll do is we'll just take this logic and put it in there. So instead of an int, this would be a t, and this would be the address of value, and we'll print value instead of that. Cool. And so what we can do again is to test our thing. It's print value and pointer of 0, and that should just print our int like we've been expecting. Okay, someone's not happy. Cannot initialize value. Oh, this needs to be const, I guess. Good. Cool. Yeah. So the same thing that we've been used to. And so, yeah, what's kind of interesting though is that when most people are talking about pointers, really they're talking about heap allocated things. So like, you know, something that gets constructed on the heap rather than on the stack. Whereas, you know, this is just a stack variable that we're making here 0. And yeah, I mean, I don't know. I think people sometimes overcomplicate pointers by thinking about it that way. Like, one way that I like to think about pointers is maybe you've got an array. So you've got an array of floats. And we'll put 10 things in the float array, and maybe we'll do print value and pointer of array. I don't know, the second value in the array. And maybe let's do the third value in the array also, just to see what that gives us. Yeah, so here you can kind of see some interesting things. So we see, oh, this isn't technically a value anymore. Anyway, so what you can see here is that when we have our second print, we're at this address in memory, blah, 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 and then 67688. And then when we do the next print, we're at 67692. So that's, what is it? Four numbers greater. We'll just call it numbers for now, so as to not get too into the weeds about what these numbers actually mean. Well, actually, you know, we should get into that. So basically what's happening, and maybe we can see this actually if we run this in the debugger, but basically these are addresses in memory that are right next to each other. So a float is 32 bits, right? We have a byte is 8 bits. So what we're actually seeing with these numbers is the address in bytes, right? So this address here, well, now it's 40380, is 1 byte after 40376, right? And what that means is that these float numbers are sequential in memory to each other, right? And we can maybe see that actually if we look in the memory view here. So let's, yeah, let's see if we can actually go to this address in memory. Okay, it's not happy. Unable to read memory. Okay, yeah. Maybe that didn't work as well as I'd hoped. That's okay. Yeah, I haven't totally figured out the memory view in C-line here, but actually maybe we can do it this way. Show in memory view, perfect. There we go. All right, yeah. Oh, I see why. It's because this is this should be in hexadecimal, and then this would understand it. So okay, yeah. So we can see here that this is our array in memory. So we've got our first number stored in these. So this is a byte, 2, 3, 4, 5, 6, 7, 8. So that's 8 bytes. So that's the first number in our array. And then right next to that in our array is the next number, and so on. And so, you know, if we actually put numbers in this array, let's do that now. So we'll do 0, 1, 2, 3, 4, and 5. There we go. All right, and let's run that again. Oh, actually, I forgot to run with the debugger. Yeah, so now we're actually seeing where these values live in memory, which is useful, and we'll tie more into the pointer stuff that I'll be talking about in a second here. So yeah, now if we look in memory, here's our array. So the first number is 0. The second one has this value 0000803F, which I guess is the floating point representation for 1. Yeah, I'm not going to get too big into the floating point representations today, but we'll just say that this means 1 in floating point representation, and then 2, and then 3, and then 4. And so kind of what I wanted to point out is that these things are right next to each other in memory, which is kind of an important thing, which I'll talk more about later on. Okay, Josh is saying, I guess I've mostly thought of pointers as data that doesn't need to exist throughout the lifetime of the application. Example is in a video game. If you're on the title screen of the game, you wouldn't need to create the character until it got past the title screen into gameplay. Yeah, that's a good point. I think a lot of people think of pointers that way, and there's pretty valid reasons for that. But yeah, I don't know, it's the idea of lifetimes in C++ is a little bit odd. And yeah, it doesn't, I guess C++ doesn't really have a strict idea of lifetimes in the language. And so that makes things complicated, but like, I'll just make a little test function here to demonstrate this. So can't type today. So yeah, if we've got this function, right? So let's say I make a variable int x, or you know what, we'll say we've got a struct called title title screen or something, right? And then, well, actually I'll just make it a real struct just to make this easier to do. So if I create the title screen here, right, this screen object will be created on the stack when we get to this point in the program, right? So, you know, someone calls this function, and now this screen gets created on the stack. And then the lifetime of screen ends at this closing bracket, right? So the screen will get created on the stack here, and then it will get destroyed. Well, it doesn't really get destroyed. Basically, the stack pointer just moves away. But for the intents and purposes of what we're talking about here, screen gets destroyed when we reach this closing bracket. And so this is the idea of scope in C++. So for example, we could put this in a scope, right? And then now screen gets destroyed at the end of the scope there, line 15. So if we try to do something here, right? Something with screen, I'll just make this a function just for something with screen, right? You can't do that, not only because this function doesn't exist, but because screen no longer exists because it only exists within this scope, right? And so, yeah, I think something that's good to think about with pointers is, or when you're thinking about pointers, is like, what is the lifetime of this thing? And so, you know, does this need to be a pointer for this reason or for that reason? Yeah, and so like what Josh is saying, big collections of data that are better to free up once you're finished with them. So that's something that you can do with pointers, or you can do just with, you know, something like a scope like this. You say, okay, I no longer need this, so I'm going to let it go out of scope, and then it's gone, right? Another thing that I used to use pointers for a lot, and I don't do this anymore, is things that need to be constructed. So for example, let's say I have a struct I'll call this test struct. And it's got a non-default constructor. So test struct. And this will take a double. And this struct will have a member that's a float. Float x equals 0, I guess. And then we'll initialize x to a cast from a float, or from a double to a float. Let's see. Okay, everyone's happy with that. I guess this should be explicit, right? And then let's say we've got another struct. This is test struct 2, right? And this one, it has an instance of test struct in it. I'll just give these things stupid names for now, but I think you guys get what I'm getting at. And we want to initialize TT with some value that comes in the constructor here, right? Or maybe, well, that's not a great example because we can just do this, right? Or maybe it's actually this was something that someone was talking to me about the other day, right? Let's do a slightly different example. Maybe we'll do a uint32t for both of these, right? And then we don't need the static cast anymore. So maybe test struct takes an int as its constructor argument, right? Okay, fine, this is explicit. Maybe test struct takes an int as its argument. And so for whatever reason, we want this to be, so if int is greater than 0, then we can cast it to an unsigned integer and create test struct. But if int is less than 0 for some reason, then maybe we can't do that, and that's bad, right? So what we can do, yeah, again, this is kind of a toy example. I don't know exactly when you would run into a situation like this in a real program, but what maybe you would want to do is make test struct a pointer here. So we can make this a unique pointer, right? And then what you would do is you would do if xx is greater than or equal to 0, then tt equals make unique test struct and we'll static cast to right. So basically what we're doing here is we're saying that TT is something that may or may not exist. And so if it exists, then TT will be this object that we've created here. And if it doesn't exist because the conditions for it to exist were not met, then TT will be null pointer, right? So if you're using this, you can do something like, oh, you know, if TT is not equal to null pointer, then do something, right? And this is bad. You shouldn't do this. And there's kind of a couple reasons for that. So the first reason is that TT here will be created using heap memory. And we'll talk, I was going to talk a bit more about that pretty soon, but for now, we'll just say that we don't want to do this on the heap if we don't have to. The other reason is that standard library actually has a better thing that we can use for this, which is standard optional. Right, and I think I need to include a header for it. And I probably include memory as well, just to make sure that unique pointer works the way I want it to. But anyway, so standard optional is better in almost every way. So that's how we would use standard optional. So the syntax is almost identical. But the reason why standard optional is better is because, first of all, it's created using stack memory rather than heap memory. So actually, this is something that we can show here. Standard unique pointer TT pointer. And then I'll just do this as a second line in here. So TT pointer make week. Right. So let's make a second helper function up here. So this will be print value and pointer, but this will be for a unique pointer. So this will be value pointer, right? And so let's see. How do I want to do this? So I want to print three things. I want to print the value itself, right? So I can do that pretty easily. Then I want to point the address where it lives, right? And so that will be, what's the problem here? Doesn't like me calling star on value pointer. Okay, it's fine. Yeah, an address, and then you'll do through pointer address, right? And so that will be the actual X pointer there. But this will be, let's do a int 64t of value pointer dot get, right? And so now let's comment out these for now. Oops. Now let's actually look in our test struct here of where things live in memory, right? So we'll create our test struct to, I don't know, let's make a name for it, and I'll initialize it with the value 10, right? And so now I'm going to do print value and pointer for ss.tt. That may not work exactly. And then tt2. Oh, whoops, tt pointer. That's the name that I actually gave it. So yeah, we've got that. Why are we unhappy here? Cannot initialize that with an R value of type that. Maybe I need more consts in there. Yeah, some of this const stuff can confuse me from time to time. Okay, sure. What are we not happy about here? Static cast from const to unique pointer to const test string pointer. All right, whatever. We don't really need this. I'm not gonna bother with it. And what are we not happy about here? Oh, I got a little too fancy here. Let's just keep this a little simpler and just put just make these regular old primitive ints instead of this other struct. Yeah, and I think that'll make everyone a little happier. No, maybe not. Okay, yeah. So I need to do a similar thing for optional to be able to print this. All right, I think that'll make everyone happy, hopefully. Anyway, let's give this a try here. Cool, yeah, so so what we're seeing here is that the optional, listed optional version of this value is stored here at this 1407 something something. Whereas value, let's see, the unique pointer version of it is stored here at this other address. And let's see if we can get a better look into where these live in memory. Yeah, here we go. Okay, so let's look at SS in the memory view. So SS is our struct, right? And it's these 1, 2, 3, 4 bytes, right? If we look at TT in the memory view, this is our optional version of it. I think it's pointing to, oh, interesting. Okay. Let's see what this points to. Oh, okay. It's giving us an evaluation error, whatever. It just do that? Yeah, okay, I can kind of just do that. So it's located basically in the same memory as our struct, which is stack memory. Whereas the pointer here, let's see if we can go to this address in memory. Well, that's probably not going to get us to where we want. Okay, yeah, it won't let me access that. But let's see if we can go to this copy value. If we can go to this address. Okay, I have to do this weird syntax apparently. All right, well, it's not happy about that either. But anyway, just to kind of get to the point here, the unique pointer is allocated on the heap. So this is using heap memory rather than stack memory. And in this case, that's not really a good idea. And I'll give an example as to why. So yeah, let's do a little bit of benchmarking. This will be fun. So since we're benchmarking, I'll switch to building in, well, I should have done Ninja multi-config to begin with, but I'll do this release with debug info build mode. And so I'm probably going to need to reset everything to be able to do this. Okay. Fine. Gotta delete the build directory and regenerate it. Yeah, it's just because I switched CMake generators. But anyway, yeah, so this is kind of morphing from talking about pointers into talking about optimization. But I think it's kind of important to understand both, or I guess more what I'm saying is, if you're going to learn about pointers, I think it's important to understand sort of what that means from like a memory layout perspective, and how that affects optimization in turn, because I think that's kind of an important thing. So what I'm going to do here is I'm going to do something where we make an array. I guess I need to include array for this, but we're going to make an array of like 1 million of these test structs, right? So we'll do array of test struct 2, and we'll make, I don't know, static context for size is tn will be 1,000,000, right? Something like that. So this is our array of structs. And okay. Let's also make a default constructor just to make things a little easy for ourselves. Test struct2, this calls the other constructor with the value of, I don't know, 10 again, just something that's greater than 0 so that we get our things working. I think that'll be fine. Anyway, so we've got our array of structs, and what we're going to do is we're going to loop through it. Loop through our array of structs, and we're going to set the value of the optional thing. What's the way to do this? We're going to set it equal to 100, right? I don't know. Hopefully this will work and not just optimize directly out. Actually, here's maybe a better way to do it. And I equals 0, and this will be plus I or something. I don't know. Something like that. And then we'll do, I'll put this in the scope, which hopefully we'll see why that is later. And then I'll do the same thing with the unique pointer version of this. So instead of TT, we will operate on TT pointer. And we need to dereference it to be able to do stuff with it. And now we're going to measure how long that takes. So it'll probably be pretty quick, even with 1,000,000 things. Maybe I'll need to go to something larger than 1,000,000. Anyway, so I always forget how to do this with standard chrono. Yeah, chrono's a little hard to use in my opinion, but anyway. So okay, we need system clock, and then so this is so start equals that, and equals the same thing basically, and then we'll do duration equals chrono, I think it's like duration passed, yeah. So this will be, I'll do microseconds, I guess. And this will be n minus start. Actually, I'm going to try to make this a little bit simpler. So using chrono equals standard chrono. No, it's got to be namespace alias. Cool, namespace alias for chrono, and that'll allow me to clean this up a little bit. It'll still be rather ugly, but whatever. And so now I can print my time. So print duration microseconds, and we can just put the duration counted in there. right? And we can do a similar thing here, just to measure how long these things are taking. So just to reiterate, since it's been a minute since I set this up, basically what we've got here is we've got a struct that has an optional and a unique pointer in it. And we're going to measure how long it takes to set all of these values one after the other, basically. So yeah, let's run it. So we want to see if the optional is faster than the unique pointer, if the unique pointer is faster than the optional. And yeah, we'll talk why this happens the way it does in a second. Okay, something broke. What broke? Probably did a bad dereference or something. Come on. Now I'm in release mode, so it's going to be more difficult here. Let me take out that for now and just see if that fixes it. Because I'm pretty sure this unique pointer version is right. Well, maybe not. So this is what I call stupid debugging, where I don't want to switch back to debug mode. So I'm just commenting things out until it works. Okay, even that doesn't work. Interesting. Maybe I do need to switch back to debug mode just for a sec. This is a small project, so it'll build pretty quick. Anyway. Okay, I don't understand. Where are we going wrong here? Set a breakpoint, maybe. Okay, we don't even get to the breakpoint. All right, what's going on here? This is a little weird. It should be the first thing in the program, right? Yeah, something strange is going on here. I'm not sure I understand this. Okay. Okay, so something weird is going on when we create this array of structs. Maybe this is too large for the stack, so maybe we'll shrink it to 1,000. Although that might make our measurements kind of meaningless because it's probably too small. Yeah, so we have a limited amount of stack size, and so we might be just running past it when I try to do 1,000,000 of them. So that's another thing to put things on the heap, is if they're too big to be on the stack. So that's kind of related to what Josh was saying earlier, where if you've got like a massive amount of data, then you might want to have that on the heap rather than on the stack, just because it might be too big for the stack. And then you have your classic stack overflow, as the saying goes. So yeah, now we're getting something. So let's switch back into release mode, where we can get more meaningful numbers. Well, maybe not more meaningful. The other problem is that I'm on Clang right now, and the Clang optimizer does this thing called heap elision, which might sort of make this less of a meaningful comparison. But anyway. Yeah, so we can see here that the unique pointers are a little bit slower. And I mean, I don't know, this is kind of a silly test, so it's maybe not the best way to compare these kinds of things. But basically what's happening is that because these unique pointers are all created on the heap, the addresses of them are going to be somewhere around in memory. So let me put a little text file in here, and maybe I can demonstrate this. Memory.text. Right. So if we think about how our memory is laid out, let's say that we have address 1, right? And this is where our array is, right? And so basically all the array is just a collection of things. So usually sort of that memory will be shared. So the same address will be the address of the very first struct in the array, which we'll call struct 0, right? And again, because the struct is just a collection of things, we can use the same address for optional. Well, this will be struct 0 TT, right? And then the next maybe spot in memory will be used to store TT pointer, right? Which will be the pointer element that's in that struct, right? And then, you know, so on for the next things. So maybe this will be 3, and this will be 4, and this will be for index 1, right? And so you can imagine this would continue for a long time. But the interesting thing is, where do these pointers point to? So this is maybe address 300, right? And maybe this is address, you know, 500 or something. Like these will kind of point to somewhere in memory, and it's typically not well defined where in memory that will be. So this is something that you kind of need to think about when you're using pointers, particularly in places where performance is really important, like maybe in your DSP code, or if you're doing graphics stuff in your graphics rendering code and things like that. So yeah, we need to kind of be a little bit careful about how we use pointers. And I guess the thing I haven't mentioned is why is it slower to get something from address 300 than from address 1 or from address 3 or something like that? And the reason why, let's see if I can find this picture. Let's see, fetch Constructor. Here we go. So this is a little thing that Jeff Dean, a fairly well-known programmer at Google, put together a little while ago. And basically what he's looking at is how long does it take the computer to reference some data or to access some data that is somewhere, right? And so the first thing he's looking at here is referencing the L1 cache. So if you're thinking about a computer, yeah, maybe this will explain it reasonably well. Yeah, this is decent. So if you think about how your CPU is put together, you have your registers, which are where sort of the most used things in your program will be stored. So, you know, the program counter and things like that will be in your register. Then you'll have this L1 cache, which in this particular CPU is on the CPU core, or like they say, on chip. I don't know if that's true on all CPUs, but it is on some. And then you've got these higher levels of cache, and then you've got main memory. And so basically the trade-off here is that L1 cache is the smallest, but it's also the fastest to access. L2 cache is a little bigger, but a little slower to access. L3, again, a little bigger, a little slower to access, and then same with main memory. And so that's what Jeff Dean is measuring here, right? So he's saying to reference something in L1 cache, it takes half a nanosecond. And again, this is in 2012 on whatever computer he was using at the time. Maybe it would be a little bit different on a computer today, but you know, similar idea. So L1 cache takes half a nanosecond, right? An L2 cache reference takes 7 nanoseconds, right? Which is 14 times slower than L1 cache, right? Main memory reference takes 100 nanoseconds, and this is 20 times slower than L2 cache, 200 times slower than L1 cache. So where these things are stored in memory matters for performance. And I think that's something that's easy to forget when it's really easy to type unique pointer. Like, you know, you could imagine that maybe, like, this was actually something I ran into a little while ago. Let's just put it at the bottom here so that I don't get it mixed up with the other demo code I was writing. But, you know, a long time ago, actually not that long ago, this was a couple of years ago, right? So I was working on writing some IIR filters. So I had a struct, we'll call it IIR filter, right? And maybe you have, so this was the old implementation, right? So this is something that I had. So this was intended to be a biquad. So I have something like a standard array. And this is float, and I don't know, we'll use 3, and this is our state, right? And we have our A coefficients and our B coefficients, right? And I'm not going to get into it too deeply, but then, maybe you have some process function, right? And so we have some const input data and some non-const output data. And then we have some samples, right? So, what you'll do is you'll do something like for what's then, and then here you'll do, something with these values in this tight inner loop, right? And then maybe at some point I figured, what, it would be nice if I could do this as a multi-channel filter. So this will be IR filter new. And so now I put these in a vector, right? And so I'll say vector size equals channels, right? Whatever that's going to be, right? Did I do this right? Oh, I don't think I've included vector. Got to do that. Right, so now these things are in vectors. And the vector size will be however many channels I have. So maybe, maybe now I need an extra argument here for the channel index that I'm going to process, whatever. But now when I measure my code, everything's slower, right? And so at the time I was like, well, that doesn't make any sense. Everything's the same. I just have more things now because, now there's more of these in more different channels rather than one of these in one channel. And unfortunately, that's not the case, right? Because before, these were in arrays, and arrays are allocated on the stack. So again, these things are right there in the same memory, in the same block of memory. And my guess is what would happen is when you start this process function, you start accessing these things that are on the stack. And so if for whatever reason this entire struct was stored in some higher level of memory, sometime early in the process function, this stuff would get pulled into cache or into a nearby cache. And then you do your processing. And all of these things are, if not on the same cache line, then very close to each other in cache, right? But now when you're using a vector here, now these are all things that are on the heap, and they're not necessarily located very close to each other. So now you've got to pull things from potentially very like parts of memory that are very far away from each other, right? And so this kind of destroys what people sometimes call cache locality. And that's kind of a difficult thing to reason about a lot of times in C++ because it can be hard to know, where your things are located. So, one thing that I do if I really do need this pattern where I need some dynamic number of channels, then I'll use this little helper thing. Someone told me about this and I forget who. I should try to remember because it's kind of important and I'd like to give them credit. But basically it's this thing called scoped value. And it's this little, what they call RIAA data struct that just stores a temporary. And then when it goes out of scope, then then it resets the value that it had. So what I would do, for example, is I would do auto state, well, maybe I wouldn't do auto here. I would use scoped value state 0 is state 0, right? And so now I've got the state 0 value on the stack, and I can work with it very efficiently. And then when I hit this, actually, sorry, this would be outside the loop. Yeah, you want this outside the loop, so you don't need to recreate it every time. So I'd have this outside the loop. This gets created as a stack variable, and then when you hit this bottom bracket, then it gets stored back in the state vector. So now instead of jumping around all over your memory, you've got this thing in local memory that you can work with, and then you only need to interface with the memory that is stored somewhere on the heap. You only need to interface with that once when you create this and once when you release it at the end of the scope. So anyway, sorry, I got a bit off topic, I guess. We were originally just talking about pointers, and then I kind of went off on this tangent of memory and where things are stored in memory and stuff like that. But this is stuff that I find interesting and that I think is important for writing stuff that is fast and writing code that is optimized. Yeah, I think, like, in particular, this latency numbers chart is really interesting because I think, when a lot of people think about optimization, they're thinking about how do we reduce the number of multiplies in our code? How do we reduce the number of divides in our code? How do we use an approximation? So instead of calling standard tanh, I have some super fast approximation that is pretty close to tanh, but is much faster. And those things are all very important. I definitely agree with that. But they're not the only thing that's important when it comes to optimizing your code. So these are definitely things that if you're interested in optimization, you should be thinking about. Maybe some of the stuff at the bottom doesn't matter so much, like, I don't know who in their plugin is sending packets from California to the Netherlands, but things like how long does a main memory reference take versus an L1 or L2 cache reference, that's kind of an important thing for folks who are doing DSP stuff, especially since you've got these really tight inner loops a lot of times. Yeah, so anyway, that's just something to think about. Yeah, another thing I've been thinking about recently is the idea of structs of arrays versus array of structs, but I don't know if I want to get into that right now because that's a kind of a whole other thing. Yeah, you know what? Let's do another test here. So this has taken like 170 some microseconds. Let's change this to a vector. Right. Right, and so we'll do, I'll keep the name just because I don't feel like changing. Array of structs dot resize. This will be size n, and we'll use the default constructor. I think it'll let us do this. But yeah, so I'll put this in my notes here. So we were at 171 microseconds or 174 microseconds for the unique pointer. Let's run that. Someone's not happy. Let's also comment out this code just so it doesn't confuse the compiler or anything. All right, what am I doing wrong here? Well, anyway, I just do that. All right, that's probably going to crash, but we'll see what happens. Oh, okay, cool. Yeah, so now we see something really interesting, right? So this is with an array of structs, right? This is with a vector of structs, right? So 684 microseconds or 758 microseconds, right? So this is the only change we made here, was moving from an array, which is something that gets allocated on the stack, to a vector, which gets allocated on the heap. And we're already, God knows how much slower. I don't really feel like calculating it. Let's do another test now using standard set. I don't use set much. Set. Yeah, okay, so set probably doesn't have a resize function here. Standard set. Oh, and set doesn't like having duplicates. Maybe let's not do set. Let's do map. I use map more than set, so I don't even use map that much, but whatever. So map doesn't have a resize function, but we'll do map some int and then stuff. So I need to include map for this to work. All right, cool. And so for int I equals 0 as less than n. This should be a side t, I guess. I'll do yeah, I really should change the name. This is definitely not an array of structs anymore, but whatever. Equals let's do test struct 2, some number. Right, and now I also need to change my loops. So I have the key, which I don't care about the name of, and I have struct, and I can do that down here as well. I think that'll work. Let's find out. Yeah, so now we're seeing something interesting. So this is with map. So map of structs 7726. So now we're getting into milliseconds. Yeah, so map is much slower than vector. So why is that? So the reason why, maybe the standard library will elucidate it for us. Yeah, it doesn't really talk about it, but basically, like a map is kind of a node-based container. So basically, you've got things pointing to other things and so on. So it's going to be slower because every time you iterate through it, you have to sort of go from one pointer to another pointer. Whereas in vector, things are all allocated sequentially in memory, which is significantly faster for some of the reasons that I was talking about before. Let's try unordered map just for fun. Unordered. I imagine this will be a little faster than map, but probably not much. Okay, yeah, that's actually a decent improvement there. So this is unordered map of structs. So we've got 2652 or 2931. So yeah, again, none of these are like especially rigorous benchmarks or anything like that. But hopefully this kind of gets across the general point that I'm talking about sort of where things are located in memory matters. The data structures that you're using matters. when it comes to performance, at least. So these are just some things to think about when you're, when you're deciding what data structures you want to use, whether it's for your DSP code or anything else that you want to be reasonably fast. Yeah, these are things that are kind of important to think about. Let's see if we can do a struct of arrays, maybe. Yeah, all right, I got an idea for this. So here's what we're gonna do. We're gonna do test struct of arrays. Right, and so what we're going to do is we're going to template this on the size. So we'll do size t n, and these will be we need the size as well. Okay. So then the question is, how do we initialize it? I'm going to do this maybe. So what we'll do is we'll just kind of do the initialization that we're doing down there, but in a loop up here. So for size t going 0 through n, we'll do I here, right? Yeah, so this is just kind of an interesting experiment to see how our performance improves or maybe doesn't improve using a struct of arrays rather than an array of structs. So let's go back down here, and now instead of our weird map thing, we're going to do test struct of arrays with the same size as before. This will be struct of arrays. And we'll construct that. Move through it here and there. This will be SOA TT. Oh, wait a second. Struct of arrays dot TT. So this will be our TT value like that. Okay, and then I'll do the same thing here with our TT pointer. Cool, what's wrong up here? Oh, I need to give these an index as well. Cool, so let's try running that, see what happens. Interesting, okay. So that puts us right here. So this is struct of arrays. 285 and yeah, so just to kind of recap, what we're seeing here is the left number is the speed essentially going through a stood optional versus the speed going through a unique pointer. And I should also mention this is without checking that the pointer or the optional is valid. It's just assuming that it is, which may or may not be okay, depending on your use case. And then what we're seeing here is as we store this data in different data structures, how does our performance change? So with an array of structs, we're seeing our best performance. With a struct of arrays, we're seeing something pretty close for the stood optional, something much slower for the unique pointers. I wonder why this is. I don't know. A lot of people seem to think that structs of arrays are typically very fast. Maybe there's something different about this particular instance or this particular case that's changing things. And then, we've got vector of structs, map of structs, unordered map of structs. Yeah, I maybe wouldn't put too much stock into some of these finer differences down at the bottom, because I've also been running Zoom on my computer this whole time so I can stream this. So who knows what that's doing to my computer as far as taking away resources that could otherwise be used to run this stuff faster. So these are all pretty rough benchmarks, nothing especially rigorous here, but just something kind of interesting as far as how thinking about pointers and thinking about data orientation can affect the performance of your code. Cool, yeah, I'm gonna drink some water, but if anyone's got some questions, feel free to throw them in there. Yeah, I'm happy to talk about this stuff. All right, I guess we've got no questions. So everyone who's watching perfectly understands pointers and data structures and everything right now. That's my guess, right? All right. That's good to hear. Cool. So I don't know, is there anything else that we can measure here? Anything else that might be interesting? Yeah, well, I guess then maybe the question is, if we don't want to use unique pointer unless we have to, then maybe where are some situations that we have to, where, it does make sense to use heap memory? Well, I don't know, I guess maybe I think of unique pointer and vector as kind of going along the same lines in that sense, the difference being that vector is more than one thing and unique pointer is just one. But yeah, so maybe let's try to make another thing that is useful to test for this. So this will be struct with pointer. So yeah, I guess one case where you might need a unique pointer is if you've got a base class, right? So maybe you've got some base class, and then you've got some derived class, right, which derives from the base class, right? So this is like a classic sort of polymorphism thing. And so then maybe you would want a member variable in your struct that's a unique pointer to the base class, right? So this will be, I don't know, let's call it pointer, right? So yeah, and then the advantage here would be that this struct doesn't need to have any knowledge of the derived class or anything like that. You can define your own derived class if you want, but it's still possible to make this be equal to, or make this pointer point to some derived class from the base class, right? So this is like a polymorphism thing. And this is also why sometimes you'll hear people talk about polymorphism as something that can potentially slow down your code, because yeah, from like a code perspective, it's nice that you can do this. It's nice that, you have some base class functionality that the derived class can implement, and, the pointer here doesn't necessarily need to know about the details of the derived class. But it's also potentially something that could make your performance a little bit worse for the reasons that I've been talking about here, as far as memory layout and where things are stored in memory. So this is an example of a place where, you might want to use a unique pointer if your performance maybe doesn't matter that much. But I mean, I don't know, performance kind of matters everywhere in my opinion, but I don't know, that's a different conversation. But maybe, the library that you're working with kind of forces you to do things in this way. So maybe you don't have a choice. I know there's some spots in Juice where you kind of have to do things this way. And I think it's okay. I guess something that I should mention too is that I think it's okay to do things like this the higher up you go, right? Like, for example, if you do this at some high level, but then all of your low level operations are really fast within the derived class, let's say, and your memory layout within the derived class is very tidy, then this isn't so bad because you have one pointer dereference to get to your derived class, and then everything in there is really quick. The problem is when you build up these big hierarchies, and then you have something like the map or the unordered map example that we were looking at, where you're pointer chasing to get to the things that you need. And that's where we run into performance issues, as you can see here with some of these timings that we're seeing. Right. What are other cases where you might want to use pointers? Let's see. Yeah, so if you do want to use something as heap memory, then that can be a good thing to do as well. And this can actually be something that you can do in kind of the structive array style that we were talking about here. So for example, let's see if we can do this a different way. So this is potentially another way to do the structive arrays. So we'll call this structive arrays 2, right? And we're going to do this a little differently. Instead of doing, I'll keep the optional stuff the same just because I don't feel like messing with it right now. But instead of this unique pointer, we'll just use a regular pointer, right? Oops, I got that on the wrong side there. We'll just use a regular pointer. And then what we'll do here is we'll set it down here. So what we'll do is we'll make a, what do we think, array or vector? Let's do an array. An array of, what was it, uint 32. And so these are int. I'll just call this our int pool. I don't know if that's the best name for it, but whatever. But then what we're going to do is we're going to set this array of pointers as pointing into this pool here. So what we'll do is we'll do for star, I don't know, also I call it t-val in structive arrays. Oh, I also need to change this to structive arrays dot tt pointer, right? And so we'll say that, let's need a counter here. There's a better way to do this, but it requires bringing some other stuff that I don't want to bring in right now. So we'll say this points to the address of int pool of count ++. Yeah, so basically what we're doing is we're putting these, I guess this needs to be a reference to a pointer or something, pointer reference. I always get confused by that stuff. But anyway, basically what we're doing is we're taking the pointer values in the structive arrays and we're assigning them to the values in this pool. So you could think that in a more real life example, this would be a memory pool of, let's say, let's say you were doing a bunch of IIR filters and you wanted them all to use the same memory. You can make just a giant array of floats and have all of the IIR filters draw from the same memory pool to access those floats. And so now we should be able to run the same benchmark. And yeah, let's see how that does. Interesting. All right. Yeah. So this is maybe somewhere around here, right? So this is struct of arrays with a pool, we'll say. So we've got 5, 85, and 370. Yeah. So here we see some of the issues in our timing, because between struct of arrays and struct of arrays pool, I didn't change anything in the optional case. So obviously there's something that's a little bit throwing off our timing here. But what's interesting here is that this is the first case where we see a pretty significant improvement between the standard optional things and the pointers, right? And so I'm wondering, does anyone have a guess as to why that is? I have a guess, but I'd be curious if anyone else has a theory on it. Open my window here real quick. Cool. So kind of what I'm thinking as far as why this is faster, right? Let's put another whole bunch of dots there, right? Is that when we've got our struct of arrays of standard optional, right? So optional has two things in it. So in this case, we've got an int, right? We got an optional int, right? So if we've got our first address, right, this is going to have two things. This is going to have the int, right, which is 32 bits, and then it's going to have a bool to say whether or not this has a value, right? So that's maybe I'm guessing the exact size of this will differ depending on the standard library implementation. Maybe, I don't know, maybe it's consistent, but maybe this is 1 byte, or maybe it's packed in some way. Right. And so basically what the computer has to do is it's got to look at this int, and then it's got to do something else, and then it's got to look at the next int, and so on. But it basically has to skip over these bools in memory, and then go to the next thing, right? And it's got the same thing, right? So our memory isn't perfectly sequential between these ints that we're looking at, because we've got these bools in between, which are taking up some space and potentially moving things off the end of the cache line, for instance. Whereas our struct of arrays of int pointers, right? Because we're pointing into this pool that is here in stack memory, and these are all sequential, right? So basically, the memory layout for this is just looking at int the whole way down, right? So that's kind of nice, because even though we're going through a pointer, the memory that we're looking into is all sequential. So anyway, I feel like my explanation for that wasn't great, but hopefully hopefully some of it makes sense. But yeah, so this is a place where pointers can be an interesting thing to do, because you're pointing into some memory that is efficiently allocated or something like that. What time are we at? Okay. Yeah, if we had a little more time, maybe I would put together a little example audio plugin of some filters that are using this kind of memory layout with a pool. But I don't know. I don't know if I've got time for that today, since it's already after 11. at least where I'm at. But yeah, I don't know, maybe I should just do some questions or see what other folks are up to here. Anyway, yeah, I'm glad I talked through some of this stuff because stuff I've been thinking about, but it helps to put it into words sometimes and just kind of, you know, experiment with some things and go from there. But yeah, this has been fun. So yeah, I guess I'll wait a few more minutes for questions and maybe I'll think about some other experiments I can run here while I've got some time. Actually, maybe I'll show you all how I do this scoped value thing. So I've got the scoped value that we were talking about here. And then if I look at my filters, this is my state variable filter implementation, which is based on one of Andy Simper's papers. Make this a little bigger too. Maybe that's too big. Yeah, so like the filter state is in these IC1 and IC2 EQ values. And so we can put those in these scoped values, do some work with them in this internal, tight inner loop. And then at this closing bracket, they get put back into their heap storage. So yeah, I found that that's a good bit faster than going back and forth to the heap storage whenever you need to do something. But yeah, so that kind of thing seems to pop up a lot. But yeah, this is just DSP code. Cool. Yeah, someone says thanks for watching, guys. Yeah, this is fun stuff to talk about. At least I find it fun. I don't know, maybe other people don't find it so fun. Actually, this is kind of an interesting thing that I was working on the other day. Maybe people are interested in it. So this is a way of iterating through an audio buffer. So you can use it with a juice audio buffer or with this buffer view type that I've been working with more recently. But basically you can iterate through the channels like this. And so sample data originally was going to be just a pointer into the buffer data. But then I figured out that you can actually use a span for this. So span is a C++ 20 thing, if I remember right. I think most compilers support spans now for C++ 20, but if you're using C++ 17, then it can be a little more difficult. But there's a separate library that implements it for people who aren't on C++ 20 yet. So that's this non-std span that I'm using here. Actually, it's a span light, if I remember right. Yeah, span light. So this is a really nice library if you're not on C++ 20 yet, but you still want to use span. Highly recommend it. But yeah, so this is kind of a neat thing. So you can iterate through your buffer. There's a bunch of other like weird template stuff that needs to happen for that to work. But basically you can iterate through your buffer channels. So I found that to be kind of a useful pattern lately. But yeah, let's see. How are we doing on this side? Yeah, maybe I'm gonna call it a day here. It's almost 11:15 where I'm at, so I'm gonna oh, okay, we got a couple questions. How is span different from a pointer? It's a little different. It's not that different, I guess is the first answer, but basically it's like a pointer plus a size or a start and end pointer, I guess, depending on how you might want to implement it. Maybe the standard library has an example implementation here. Okay, now they've got examples, but they don't have a example implementation. So the nice thing about span is that it's basically just like a regular container. So you can do things like iterate over it with, like the begin and end iterators. You can do like a range-based for loop. You can do things like front and back. You can do regular array access, just like with a pointer. But the big difference between a pointer and a span is that you've got the size. So like with a pointer, you need to also keep, like if you're pointing into an array or something like that, or you're pointing into a vector, you also need to do some manual bookkeeping to keep the size of the vector, the size of the array that you're pointing into, so that you know that and you don't run past the end of it. With span, you get that not for free, but it manages that internally. So you can just use their managed version of it rather than managing it yourself. And then you've also got this handy little subspan thing here, which is just nice for kind of getting a small part of your span if you want to do something like that. And then yeah, in C++ 23, we're going to get MD span, which I recently saw a talk that Timur was doing about MD span. So that's definitely going to kind of be an even bigger game changer, I think, with things like doing matrix operations and stuff like that. Yeah. So yeah, span is it's a little funky because you might see stuff like this and say that looks hard to use, but a lot of the stuff you can ignore often. It depends on what you're doing, but like for the stuff that I've been doing, I basically construct a span from a pointer and a size, and that gives me everything I need. So you know, you could probably implement your own basic version of span without too much difficulty, but there was this library available, so I figured I'd use that instead. But yeah, so a span is basically just like a pointer with a size to tell you how much data the pointer points to, or how many objects the pointer can point to. Well, even that's not a great way of describing it. It's like a pointer plus, yeah, it's like a start and end pointer is maybe the simplest way to go. Yeah, thanks for tuning in, man. Okay, and then Josh is asking, what are your general thoughts on external libs and dependencies? Do you tend to stay away from them or use them heavily? In the past, I've tried to stay mostly vanilla juice. I was actually talking about this with a fellow over email a couple days ago. I guess kind of the way that I think about it is I think about like, I forget the exact word I used, but I feel like maybe it's something like intrusive dependencies versus non-intrusive dependencies. And so like for non-intrusive dependencies, I use them all the time and I pull them in whenever I feel like it. And I think that's fine because like, since it's non-intrusive, I can kind of choose for a given use case whether or not I want to use them. And it's very easy to opt out of them if I decide that I don't want them for a particular thing that I'm working on. But more intrusive dependencies, like for example, juice is a pretty intrusive dependency. Like when you're writing code in sort of a juice project, there's a lot of very particular things that juice needs you to do with your code to be able to work with the juice API. And so that kind of changes the way that your whole project has to be written in a lot of ways. And so I try to be a little more careful with that kind of thing. Oh man, street cleaner's back here. Okay, just saying, what do you mean by non-intrusive? Yeah, so for example, this is a library that I use a ton. Let's find it. Yeah, so this magic enum library I use all the time. It's a great library. But what's nice about it is that I don't need to like do anything extra to my code to get it to work. So I can just have my enums hanging around the way I usually do. And then if I want to do something, like for example, get a string from an enum value, then I can just include magic enum and do this, right? So maybe a example would be helpful here. Let's God, what's it? Actually, maybe a better thing, maybe a better example would be talking about C++ reflection libraries. see. I'm trying to find, there's one library I was looking at a little bit ago that I'm trying to find. Wasn't this one? I don't think it was that one. Oh yeah, okay, this is a good example. Even though I haven't seen this one before, this is a good example. So basically, like, even this isn't a perfect example, but it's good enough. So basically, this is a library for getting reflection from a struct, right? And so in this case, we've got a user-defined struct here, and then he registers it in some way so that it can be used for reflection. And so I would say that this is a little bit intrusive because, for example, let's say you were doing this with like a juice class. You wanted to register a juice class to be able to do reflection on it. There might be some private member variables that you're not able to access to be able to register like this, right? And so in that case, or in that sense, I would say that this is kind of an intrusive dependency because every struct that you make, you need to organize it so that you can do this, this kind of thing to be able to do reflection on it. Whereas the reflection library that I use is a little bit less intrusive because you can kind of just have your struct and then do stuff with the struct without having to change it or meet any specific requirements, or there's fewer requirements. And it's not perfect, like because it's less intrusive, it's less powerful in some ways than some other reflection libraries that I've seen. But it also means that I can use it with, for example, with juice code without having to go in and change a bunch of juice stuff. Or it's a little bit easier to kind of interoperate with things. So yeah, I guess by non-intrusive, I mean that like by using the library, it doesn't force you to change a lot of code that you may have already written, or something like that. Yeah, I don't know if that's the best answer, but yeah, so I guess if it seems like a library is something that I can sprinkle in when I want to use it and completely ignore when I don't want to use it, then I have no problem pulling it in. If it seems like something that if I were to use it, I would have to write a lot of my code with that in mind, then I try to think a lot more about the trade-offs of like, well, what am I getting from this library? Is it worth having to think about it so carefully when I'm writing my code for it? Yeah, and so I mean, I guess another example would be libsoundfile, or not libsoundfile, libsamplerate. Like libsamplerate is a somewhat intrusive library in that when you're going to use it, you have to think about structuring your data correctly so that you can put it in, you can pass it through the libsamplerate algorithms. But the algorithms are so good that I would say it's worth it. And so that's why maybe you would write a wrapper so that you can interface between, say, a juice audio buffer and a libsamplerate, the libsamplerate algorithms, right? So yeah, just because a dependency is intrusive doesn't mean you should stay away from it completely. It just means that you should think carefully about what you're getting from it versus the cost of using it as far as your implementation time. But yeah, I mean, that's obviously a matter of opinion too, and different people are comfortable with different things. So yeah, it's definitely kind of up to you. Cool. All right, I think I'm gonna probably wrap it up here pretty soon, unless some folks have more questions or are curious about things. Yeah, we didn't really get into circuit modeling today. Maybe we'll do that another time. But yeah, so latency comparison, memory layouts, and performance. So we've been talking about today. So yeah, hopefully this is maybe sparked some inspiration or sparked some curiosity for everyone watching, and you'll have some ideas for how to make your code even faster and ideas for different things you can measure and benchmark when you're trying to optimize your code. So cool. All right, guys, well, I'm gonna wrap it up here. How can I get back to Zoom? Oh, stop share. There we go. Cool. All right, thanks everyone for tuning in, and hopefully I'll be back next week with another live stream.